Welcome to today's RSECTION training. My name is Sonja von Bloh. I hold the training together with my colleague Andreas Hörold. Andreas, perhaps you would like to introduce yourself.
Yeah, my name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. Yeah, I will answer your question or questions in this training.
Thank you, Andreas. First, I would like to show you how to use the training interface. The settings allow you to adjust your audio settings. There's also a chat function. You can use the window at the bottom to send us questions or comments. We try to answer these questions within the training. If there are too many questions that cannot be answered today, you will definitely receive an email afterwards. The training is recorded. This will be sent to you after the training. You also get all the models used. I would now like to give you a brief overview of the training series. In today's training, you will receive an introduction to the strengths of materials. This training builds on the first training, which explained how the internal forces are calculated. In today's training, you will learn how the cross-section values and stresses are calculated. In the upcoming training courses, you will then receive an introduction to finite element analysis and then an introduction to our design modules. This brings me to today's training program. I will first give you an introduction to the RSECTION program. Using several examples, I would like to show you the modeling options and design methods in the program. In the first example, a thin-walled eye profile is modeled with graphic functions. I will model this slowly so that you can enter this cross-section as well. In another example, I show how to insert cross-sections from the database and how you can add other parts to these cross-sections. Then I show the modeling of a massive cross-section based on a DXF template. Finally, I model a hybrid cross-section. First, I start a survey to find out whether strengths of materials has already been covered in your studies. I ask you to answer this now. Most of you have already taken classes to strengths of materials. So I close this now. And then I would ask you to answer the following survey. I will start it. If you are working with two screens or monitors, I will adjust my pace accordingly. Okay, most of you are not working with those two screens, so I will make it a little bit slower. Okay. Then I go to the RSECTION program. RSECTION is an independently executable program for generating any thin-walled or massive profiles. If you want to design special profiles in RFEM or RStab that are not contained in the profile library, you can create them with RSECTION. You can then import these user-defined profiles into RFEM or RStab. In RSECTION, it's possible to calculate cross-section values and stresses. The RSECTION user interface is the same like in RFEM 6 or RStab 9. The cross-section graphics and dialogues are displayed in the working window. Most tasks can be performed with the mouse. In the table here at the bottom, the keyboard is primarily used for numeric input and output of the results. There are three navigators here on the left of the working window. It's the navigator data, the navigator display, and the navigator results.
So, Sonja, just an interruption. We can see the PowerPoint slide and not the section window.
Ah, I will share the other screen.
Ah, that's quite better. Thank you.
Okay, sorry for that. Yeah, here on the left are the navigators, and the first navigator is the data navigator. The data navigator manages the input data. A double click on an entry opens the dialog. I can show you this now. If I double click on the point, then the dialog for editing the points will open. However, the dialogs for creating objects can also be called here. Just right click here on points, for example, and then it's possible to create a new point, for example. The display navigator here, controls the graphical display in the working window. If the checkbox in front of an entry is unchecked, this object is hidden in the graphic. If I uncheck here the points, then you will see that the points will not displayed anymore. If I check it again, the points will be shown. Then the third navigator is the result navigator. The result navigator controls which results are displayed. Then I would like to go into the mouse functions. To move the sections, you can hold down the mouse wheel and move the section accordingly. You can turn the mouse wheel to zoom in or to zoom out, and right-click to open the context menu. You can also select objects with the mouse. If you open a window from left to the right, everything that is completely within the selection area will be selected. If you drag a window from right to left, everything that is intersected by the selection area will be selected. You can also select individual objects. To do this, left-click on the object to be selected. To add objects to the selection, hold down the Control key. Here, I select the whole part. And to remove objects from the selection, hold down the Shift key. Here, I deselect the part. For the first part of the training, I'm now starting a survey again. Please answer the following questions about the suitability of our section. Multiple selection is also possible. I will end and share the results. All answers are correct. RSECTION is suited for the creation of any thin-walled or massive cross-section and also for the calculation of cross-section properties and stresses. This brings me to the first example. To create a custom profile, I open the new model dialog. To do this, I click here on this button. I first enter the cross-section name. I name it Example 1. Furthermore, the analysis method must be defined. The following analysis methods are available. It's the finite element analysis and the thin-walled analysis. I will choose the thin-walled analysis in this case. The effective cross-section can be calculated for both analysis methods after activating the extension here on the right. A standard must be selected according to whose rules the subpanels are to be generated and the effective cross-section is to be calculated. The following standards are currently available. It's Eurocode 3 Part 1.1, Eurocode 3 Part 1.3 for cold form cross-sections, and Eurocode 9 for aluminum cross-section. I choose here Eurocode Part 3 Part 1.1. The selection of
Sonja, sorry for the interruption again. Would you like to show the PowerPoint slide or the
No,
section?
I just wanted to show, yeah, maybe there's a problem with which monitor I share. So maybe yes, you should see now the dialog to edit the base data, and so maybe it's a problem. You should see it now.
Yes.
Yeah.
Thank
sorry.
You.
Yeah.
Okay.
We changed our training interface now, so I apologize for this. I have to learn it. Okay. Okay, I've chosen the analysis method thin-walled analysis here, and I've activated the add-on effective steel aluminum section, and I've chosen here the standard Eurocode 3 Part 1.1. The selection of the design method or standard is irrelevant when using the RSECTION cross-section in RFEM or RSTAB. You can select the design method in RFEM RSTAB regardless of what is set in RSECTION. Furthermore, the subpanels are generated in the design modules based on the standard selected in the design add-on. On the steel design add-on, the manufacturing type determines which part of the standard is used for the design. You can select the manufacturing type here, and here it's also possible to define the buckling curves. For a cold form sections, the standard Eurocode Eurocode 3 Part 1.3 is used, and for hot rolled or welded section, the standard Eurocode 3 Part 1.1 is used. Then I click on OK, and the new file will be created. I first define the material. For this, I go to the navigator data, and materials already been defined, and I double click on this material to modify this. I can create or copy another material in the list here on the left via these buttons, create new material or copy selected materials, or I can also delete the selected materials. I can enter a material name directly here in this box. For this, I activate this button, user defined material. And if I do so, I can enter a name. And our section then lists all materials that match that name. But I can also open the material library for a specific selection. And to do this, I have to click on this button, Import from Material Library. And in the material library, filters are available here on the left to quickly find the material. I can filter by material type, I can filter by the standard, and it's also possible to search for a material by its name if I enter here the name. I want to use an S235 from this standard. Here I choose this material and then I click on OK. If the material is not in the material library, I can create this material by activating the user-defined material checkbox. I can adjust then the material values in this tab if I want to. I don't want to use this now, so I uncheck this checkbox again. Then I click on OK. I then create the elements. The definition of elements is required if the analysis method, analysis of thin-walled structures, is selected, or if the effective cross-section is to be calculated. An element must always lie in a surface, and the surface is called part in our section. Elements can be created graphically or via a dialog. The graphical input is called up via the symbol in the toolbar, and the input via dialog is called up via the navigator data. Here I can create a new element. When creating an element via the graphical input, the part is also created. When created an element via the dialog box, the part and the points of the element must be created beforehand. This is why it's not possible now to choose here a single line, because for the single line, the points must be defined first. So I use the graphical input, and here I choose single. I'll enter the bottom flange here first, and for this I use the input mode length and direction. I can also define an angle on the work plane. This angle should be 0 degree, and I define here the length. This should be 150 millimeter, and the thickness should be 10.7 millimeter. Then I place this element here by clicking with the left mouse button. Then I create the web. Elements must be connected for the calculation of the effective cross-section. The connection is to be made via the start and endpoints of the elements. If two elements share the same points, they are connected. I use here also the input mode length and direction, but the web has here an angle in the work plane about 90 degrees, and it has a length of 289.3 millimeter and a thickness of 7.1 millimeter. Then I want to reverse here the direction, and I choose here this point. Then I create the left flange. For this I use also this input mode. Angle on work plane is 0 degree. The length is 75 millimeters and the thickness is 10.7 millimeter. Then I reverse the direction, the orientation of the element, and then I create here the right flange. To close the dialog, I can click on the right mouse button. The cross-section should be a rolled T profile to which a lower flange is welded. The round radius is 15 millimeters. I can define lines to create them or use the create round corner function. In this case, I create the round radius using the function, and you find this function here in the bottom. Create round corner, and then I have to define the round radius. It's 15 millimeters, and then I have to click on the relevant lines. Then I click on the right mouse button to close the dialog again. The lower flange is welded with a 6 millimeter double fillet weld. I create the welds using the create angled corner function. You find this also here in the bottom, create angle corner functions. And here I have two corner types, both edges and edge and angle. And here I choose the corner type edge and angle. You can also calculate in the dialogues. So I define here 6 multiplied by square root of 2. And the program now calculates the lengths L1 to 8.49 millimeters. Then I have to define the angle. It's 45 degrees. And then I have to click on the relevant lines here in the bottom. And with right mouse button, I close the dialog again. The sub-panels that you can see here are automatically generated based on the standard selected in the base data dialog. These cannot be changed. If no elements are defined, a cross-section classification in RSECTION and the design modules of RFEM or RSTAB is not possible, and neither a calculation of the effective cross-section is possible. In the design add-ons, this cross-section is then designed according to the cross-section class 3. I would also like to use this example to show you how to calculate stresses and the effective cross-section. in order to calculate stresses or the effective cross-section, a load case must first be created. Load combination can also be found. First, I create a load case, and I do this via this navigator data. Here, I right-click on load case, and I choose here new load case and combination. Then I give the load case a name. This is called N, and then I want to create a second load case, and I do this by pressing this button, Create New Load Case. And I give the load case name MY. I want to create also a load combination. To do this, I click here on New Load Combination, and then I choose here the relevant load cases. If I want to choose all, I can click on this button, Add All. It's also possible here to change these values. Then I click on OK. And then I have to define the internal forces. The internal forces can then be defined manually or imported from RStab or RFEM. Only an import from RStab 9 or RFEM 6 is possible. The RFEM 6 or RStab 9 file must be saved with results. I define the internal forces manually today. To do this, I go to the navigator data and I open here the tree internal forces, and I double click on internal forces to open the dialog. Here I define an axial force of minus 10 kilonewton. Compressive forces are negative, tensile forces are positive. The axial force acts in the center of gravity of the cross section. Then I click on Apply and Next, and I choose the second load case, MY, and here I want to define an axial force of 0 kilonewton, and I define a bending moment about 100 kilonewton. I don't want to define it in kilonewton centimeter. I want to define it in kilonewton meter. I can add this manually, but it's also possible here to change the units and decimal places. And I want to do this now. So I choose here kilonewton meter. And then I define here 100 kilonewton meter. Then I click on OK. The blue dots that you can see here are the stress points. Stresses are calculated and displayed at the stress points. The stress points are generated automatically. Stress points can also be defined manually. I want to do this now here. And to do this, I go to the navigator data again, and I right-click on stress points and choose here new stress point. I define the stress point number. This should be 100. And I define the stress points coordinates, and this should be 75 millimeter and minus 100 millimeter. And then I click here on OK, and then this stress point is generated here. Which stresses are to be calculated and output in tabular and graphical form can be set in the stress configuration. You find the stress configuration also here in the navigator data. Here under stresses, stress configuration, double click opens the corresponding dialog, and here you can choose on activating or deactivating a checkbox with which stresses have to be calculated. I'm satisfied with the predefined, with the default setting, so I click here on OK. Then I start the calculation now. I click here, calculate all, and now the cross-section properties and stresses are calculated. In the results navigator, you can switch between the gross cross-section and the effective cross-section. Here, thin-word analysis is for the gross cross-section and effective thin-word analysis is for the effective cross-section. The same is possible in the table. You can here switch between thin-word analysis and effective thin-word analysis. It's also possible to choose here or switch between the load cases and combinations. I choose here load case 1 for compression, and I check here the thin-word analysis, the gross cross-section properties, and here sectional area is calculated, bending area moments of inertia about y-axis and z-axis are calculated. Here I can see that the sectional area is about 54 square centimeter. If I choose here the effective thin-word analysis, oops, I see it here now. It's the same. This should be different. Maybe I did an error for the material. I think a different material should be used here, but it's good to show you how you can add the material that you have defined. To change the material, you can double click on this material, and then I open the material library again, and instead of an S235, I wanted to use an S355 material. Then I click here on OK, and I start the calculation again, and now I get the expected results, and you can now see that the sectional area is about 52 square centimeter, what's lower than the sectional area of the gross cross-section. This cross-section falls into class 4, and the classification, you can see this also here for the effective thin-word analysis, the section classification, and you can see here the cross-section is classified as class 4. And you get here detailed information about the classification. And you see here that this subpanel, you can select it, falls into class 4. It's the web. And here you can see also the reduction due to local buckling. I want to show you also that you can change the type of display. Now isobands are defined here, and I can turn it off. And now here the stresses are shown in different way. It's also possible to view the statical moments graphically and also numerically here on the tables. you can select here statical moments and warping, and it's also possible to see the numerical results of the stresses. I want to show this here. I choose here the stresses, and it's also possible to show the stresses by stress points. And we have created, I don't see it because of the subpanels here, so I deactivate the subpanels here, but oops. And then I click on the manually defined stress points, stress point number 100. And if I do so, you can see here the results of this stress point. I'm now starting a survey again regarding the requirements for a cross-sectional classification. Multiple selection is also possible. Oops. Unfortunately, now I have problems with my mouse, so now it works. And now I launch the poll. Now I end and share the results. All answers are correct. For a classification, internal forces must be defined, elements must be defined, and it's necessary to activate the effective section add-on. I would now like to use another example to show you how you can access cross-sections from the library and modify them. For this, I create a new file, and I do this via this button, New Model, and I name this file Example2. I select the analysis method, thin-walled analysis, and I activate the calculation of effective section according to the standard Eurocode 3 part 1.1. Then I click here on OK. I go to the navigator data, and then I define the material. For this, I double click on the material that's already defined. And now I want to create an S235 material. I import this material from the library. Here I choose the desired material and I click on OK. Then I insert a cross-section from the cross-section library. To do this, I go here to the navigator data again, right-click on section, new section. The window is structured like the material window. A cross-section can be created or copied via the list, via these buttons here in the bottom. I can also enter the name directly here, or it's also possible to open the cross-section library via this button. A large number of cross-sections have already been entered into the cross-section library, and I choose here an L profile. And here I have also filters. I can filter the manufacturer or the standard and so on. And here a search option is also available. And I want to use this now. I enter here L200, X 150, X12. And I choose then this cross section and I click on OK. The angle should be mirrored around the y-axis. That's why I activate this checkbox, and it should also be rotated by 90 degrees. So I define here 90 degrees. Furthermore, I select the offset point on the graphic. To do this, I zoom into the graphic and I select this point. At this point, the cross section is placed at the insertion point. The insertion point can be defined here. I then pick the insertion point in the working window, and I will do this here. And then I click on OK. When inserting this thin-walled cross-section, two elements have been defined. You can see this here, and also the part is created. The cross-section can be subsequently edited, moved, mirrored, or rotated via these options. It's also possible to open the edit section window again by double-clicking on the section. However, in order to modify individual objects such as points or lines, the cross-section must be splitted. The cross-section is to be supplemented by further cross-section parts. I therefore split the cross-section into its individual parts for further processing, and to do this, I right-click on this section, and then I choose here section explode. The fillet isn't needed, so I remove this by clicking on the delete button. I also add more elements. I insert an element here via the graphical import. I choose here single, and I choose the input mode length and direction. Here I have to reverse the orientation, and then I define a length about 200 millimeter and a thickness about 12 millimeter. And then I click on this point. And another element has to be created. So I want to create the web now. For this, I choose the angle on a work plane about 90 degrees. Then I have to reverse the orientation again. And I define here a length about 400 millimeter and a thickness of 10 millimeter. And then I click on this point. I also delete unnecessary lines. Here's a line. To see it better, it's possible to deactivate here the elements and the parts. Then you can see here's a line that I don't need. So I can delete it. I don't need this line. So, sorry. Make it back. And welding seams should be also taken into account in the cross-section values. And I create the welds using the angle corner function that I did before also in the past example. So I choose here this function, create angled corner. I choose the corner type edge and angle. And I define a 6 mm double fillet weld, so that I define 6 multiplied by square root of 2. I define the angle about 45 degrees, and then I click on the relevant lines. Furthermore, I still have to create the part by selecting the lines. We have here a function that's called select boundary. Here I click on OK, and then I click on line, and now the RSECTION recognizes this that the polyline is closed and creates then the part. I would now like to calculate the effective cross-section and the stresses so that I can create load cases and internal forces. For this, I define the load case first. I go to the navigator data, right-click on load case, choose new load case, name the load case M. Then I create a second load case, MY, and I also want to create a load combination. For this, I click on this button, Add Load Combination, and I want to consider both load cases in my combination. So I click on OK. Then I have to define the internal forces. In load case 1, I define minus 50 kilonewton, apply and next. Go to the next load case. Here I define an axial force about 0 kilonewton and an MY about 20 kilonewton meter. And then I click on OK. Then I start the calculation. And I want to see my results. I can see the effective cross-section now, and this cross-section is also reduced because web here and the flange here fall into class 4. I can control this also here on the table below. Go to the section classification, then I click here on the sub-panel. I can see here that this sub-panel falls into class 4. I can also see here the details also for this sub-panel. This is also class 4. And I can also see the effective widths for these sub-panels. Here I can control the effective widths and the ineffective widths. It's also possible to see the effective cross-section for this load case 2. Here only this part falls into class 4. And I can control also here the load combination. I want to create also documentation, and this documentation in our section is called a printout report, and I want to show you this now. For this, I go to the navigator data again, and here are the tree for the printout reports. To create a new printout report, I right-click on printout report and choose new printout report. And then it's possible by activating or deactivating the checkbox in front of the report items to choose which item should be in the printout report. I don't want to have the unit normal stresses and unit shear stresses in this printout report, so I deselect this. Then I go to Save and Show, and the printout will be created and shown. It's also possible to insert graphics to this printout report. To do this, I go here to this button and choose a Print Graphics to Printout Report. Here you have various settings for the scaling and so on. I choose here a Windows filling, and then I click on Save and Show. And now this result graphic is inserted in this printout report. I'm starting a poll again. Please answer if an analysis of thin-walled structures is suitable for the calculation of rolled parametric steel sections. All of you gave the correct answer. The correct answer is here that the analysis of thin-walled structures is suitable for the calculation of rolled parametric steel sections. Close the poll again. In the next example, I would like to show you that you can also create cross-sections by importing a DXF file. The DXF file can be imported via the File menu, File, Import DXF. Then you have to choose the corresponding DXF file. Then I click on Open. I don't want to import the DXF file into the active model. I want to create a new one, so I click here on No. In section Create Section Model here, you have three options for creating the cross-section. The automatic creation of elements is useful if the outlines of the cross-section are available in the DXF file. Our section attempts to create center lines for parallel lines and then set the elements between the intersections. Only elements that do not exceed the maximum thickness that you can define here are created. The import function use DXF template lines as center lines is useful if the cross-section geometry is available as a center line model. The lines of the DXF templates are considered as the center lines of the elements. The thickness defined in the field T is assigned equally to all elements. Then the third option, create DXF templates, is used for massive cross-sections where no elements need to be created. In addition, this function can also be used for complex cross-sections where I only want to create elements for the decisive cross-section parts. With this import function, the lines in the DXF file are imported as lines. You can then use these lines as an aid for modeling. So I choose here this option for the creation of the lines. Then I click on OK. A finite element analysis is to be carried out on the imported cross-section. I control this in the base data. Here, the analysis method finite element analysis is already chosen. So I click here on OK. A finite element analysis should be performed on massive cross-sections, such as timber cross-sections or concrete cross-sections, in contrast to thin-walled cross-sections where the stresses can be regarded as constant across the cross-section thickness. The stress distribution in solid cross-section is variable. This can only be determined via a finite element analysis. Then I define the material for this cross-sections. For this, I go to the navigator data again. I double-click on this entry, and I open the cross-section database, the material database. And here I choose AW6060. And then this material. Then I click on OK and OK. In a finite element analysis, only a surface needs to be defined. The surface here is called part, and no elements need to be defined. I would only have to define elements if I also want to calculate the effective cross-section or carry out a classification. So I only have to create the part here, and I create this via this function select boundary. Here I click on OK, and then I select the boundary lines. After creating the part, I still need to create the openings. I create the openings also via a function that's called select boundary for openings. And then I click here on the relevant lines. It's also possible here to click on these lines, but I want to show you an additional function. I can create these openings also by rotating and copying this opening. And for this, I select this opening. And then I choose here the function rotate selected objects. I want to create a copy, so I activate this checkbox. I want to create 3 copies. Rotation angle is 90 degrees, and I pick the point of rotation. That's here, and then I click on OK. And now the openings are created. I want to calculate the stresses here as well. So I create a load case, new load case. I name this load case M. I create an additional load case, MT. And Then I create also a load combination where I want to put in all load cases, and then I click on OK. Then I have to define the internal forces. I open the corresponding dialog, and I define an axial force of minus 10 kilonewton. Click on Apply and Next. I choose then the load case 2. Here I define 0 kilonewton and torsional moment about 0.3 kilonewton meter. And then I click on OK. Then I start the calculation, calculate all. And I want to see here the stresses for my load combination. I choose here the stresses that I want to see. And I want to also create a printout report and insert the result graphic. For this, I go to the navigator data again, right click on printout report, new printout report. I don't want to have the unit normal stresses and unit shear stresses in the printout report, so I deactivate these items. Click on Save and Show. And then I want to insert also this graphic to this printout report. So I choose here Print Graphics to Printout Report. Window filling is activated, and then I click here on Save and Show. And now I can see here my result graphic is also inserted into this printout report. I'm starting a poll again. Please answer whether the finite element method is suitable for the calculation of solid cross-sections, such as concrete or timber cross-section. So I start this poll again. Okay, I now share the results. Most of you gave the correct answer. Correct answer is here that the finite element method is suitable for the calculation of massive cross-sections. I close the poll. As a last example, I show the modeling of a composite cross-section. In our section, it's also possible to model cross-sections that consist of different materials. Ideal cross-section values are determined for such cross-sections. 1000 millimeter wide and 200 millimeter high concrete cross-section lying on a HEB steel cross-section is modeled. For this, I create a new file. I go here to a new file. I name this Example 4. I choose here the analysis method, finite element analysis, and then I click on OK. Then I have to create two materials. First, I create the first material. It's a steel material S235. I choose this from the material library. I choose here S235. I want to have it from this standard. Then I click on OK. Then I need a second concrete material. For this, I create the second material via this button. Go to the material library again, and then I enter here C4050, and I want to have this from this standard, and then I click on OK. First, I model the concrete cross-section with the dimension B2H 1000 to 200 millimeter. To do this, I choose here the rectangle part. I choose the relevant material. It's material C4050. Click on OK. Then I zoom into the graphic and I choose here, minus 500 millimeter, minus 200 millimeter as the first point, and as the second point, I choose here Y 500 millimeter and Z 0 millimeter, and then I close this, and then I create the section. To do this, I go to the navigator data again, right click on section, new section. I open the cross-section library via this button, and then I choose here HEB 400, and this HEB should have this material 1 S235. I click on OK. Then I choose the center of the top flange as the offset point here in the graphic, and I choose here this point as the insertion point, and then I click on OK. I now create a load case bending moment M. To do this, I go to the navigator data again, new load case, M, click on OK. Then I have to define the internal forces for this load case. I open the dialog again. Bending moment should be 100 kilonewton meter. I click on OK and start the calculation. I can see also here the stresses, and I would also like to show you how to import the cross-section into RFEM. To do this, I save the cross-section. I now open RFEM. And I import the cross-section into RFEM. I've already created a file here, and here I go to the navigator data, go to section, new section. Then I open the section library, and I want to import a cross-section from our section. And to do this, I click on this button here. And then I choose the cross-section that I want to import. To do this, it's necessary that here the folder is in the project navigator. I've already done this beforehand. If you want to do this, you can add an existing project to the project navigator, or it's also possible to create a new project. I choose here this example 4, click on OK, And now this cross-section is imported. And here the option hybrid is already activated. That means this cross-section consists of several materials. And here in the tab hybrid, it's possible to assign different materials to the parts if you want to. Then I click on OK, and then it's possible to use this cross-section in a member. And to create a new single member, I click on New Member. Then I choose this cross-section, and then I can create this member here. With this example, I have come to the end of the training. It was taught how you can create general cross-sections with graphic functions, how you can add cross-section parts to database cross-sections, and create a cross-section based on an DXF import. Finally, I would like to show you where you can find more information. For this, I go to our website. On our website, you will find frequently asked questions. You can find it here in this tab, Support and Learning, frequently asked questions, knowledge base. It's also possible to go to news and events and to look for webinars and so on. I hope that the training for using our section has helped you, and thank you for your attention.
Thank you. Bye-bye.